Welcome to part 2 of my video on the McCabe-Thiele method. What we've been working on up till now has been pulling together the various constraints on binary distillation, things like the mass balances, the modeling as equilibrium stages, breaking the column into the upper part enriching and the lower part stripping sections, and finding the operating lines. Then the fact that the operating lines would meet at the feed tray. And we have one more constraint to talk about, which is the conditions of the feed tray, the feed stream itself. So in this part of the video, we're going to go through that and hopefully get all the way to the end to show how the McCabe-Thiele method works. So here's a summary of what we've found so far of those same constraints. Relationship between the flow streams. We're going to have the equilibrium data is given on this XY diagram. Then the operating line equations, which have a slope of, in this case, L over V, which are the liquid and vapor flows in the upper part of the column, and the liquid and vapor flows in the lower part of the column. And then the conditions where the two meet at the feed tray. So we need to talk next about quality. So what is quality? So when we actually build and operate a distillation column, we have to know what's going on with the feed. So there's going to be some unit inside the column that is the feed tray. And this feed tray will also be an equilibrium stage, but it will have an extra side stream with a feed F and a mole fraction of species A X sub F. Now, this feed condition may be saturated vapor, saturated liquid, or a mix as three possibilities. And we're just going to talk about those three cases together. So if it's a mixture of saturated liquid and vapor, then we can just in our minds mentally put it through a flash calculation. So there'll be a certain amount of vapor that it divides into and a certain amount of liquid. So this is the liquid in stream F and the vapor in stream F. And these will both be the conditions of whatever the feed tray condition. So I'm going to say, just for the purposes as I did in the first video, I'm going to call the feed tray number 4. Just so that I don't have to call it, sub F or something. We'll call it 4 for now, and then we can drop that later. So remember, when we have an equilibrium tray, we have a composition in the liquid phase, XF, and a composition in the vapor phase, X4, Y4. And so that means that the composition here of the liquid phase is X4, and the composition here of the vapor phase is Y4. So now let's define quality. So quality is the ratio of the liquid in the feed divided by the total flow rate of the feed. So from that, we could also say calculate the vapor in the feed as F minus LF. And then we can see that that must just be 1 minus Q. So that's all it is. We've just organized the possible condition of the feed into this through this variable or this quantity Q. And so VF is 1 minus Q times F, and LF is just Q times F. So those were the things that we needed. So this Q, notice that when there's no liquid, Q is 0. And so that means it's a saturated vapor. And when there's no vapor, Q is 1. So the Q goes between 0 and 1. There are other values, but we're just sticking with the simplest case right now. So now this feed tray is part of our overall column. and it comes in here in the center, and so it has to merge with the rest of the column. So let's see what conditions that brings about. So if we have this feed that's partially liquid, so we have this liquid flow coming in, we can just pull all the liquids together. And what we've been saying is that the liquids at the feed tray, the upper part of the column will bring in an amount L of liquid, and the lower part of the column will take away an amount L bar of the liquid. And we can do a quickie balance on this. Okay, so in minus out, LF plus L is equal to L bar. Okay, so LF is equal to L bar minus L. And for reasons that'll be handy to us, we'll use minus LF equals L minus L bar. And just from our previous page, LF is Q times F. So this minus Q times F is equal to L minus L bar. We can do the same for the vapors. So the VF goes in, and we can add up all the vapor streams. And so coming from the bottom of the column is a vapor stream of that many moles per hour. And going out is the V. And we have the same kind of a balance. So in is VF, and in is V bar, and out is V. And so VF is equal to V minus V bar. And going back again here, VF is 1 minus Q times F. So 1 minus Q VF, excuse me, 1 minus QF, slight typo there. One minus QF is equal to VF equals V minus V bar. So this little exercise where we considered the feed, conditions of the feed, and wrote it in terms of quality, has allowed us to express these differences between the molar flow rates at the top and bottom of the column. And that's going to allow us to return to another calculation we had from the first video, where we considered this condition at the feed, and we asked the question, what would happen if the passing streams of the feed happened to be, if the liquid flow composition had to be XF? And we got this far, and then we kind of stalled because we couldn't say much about L minus LF and V minus, excuse me, L minus L bar and V minus V bar. Well, we're in a much better condition now because we just wrote on our previous sheet about those L minus L bar. So we can now write this expression in terms of Q and get a more definitive answer for what the Y would be at the feed tray when we choose to make the X XF. So let's just fill that in. So we're going to return. And just for the future, I'll just say see page 11. All right, and so here we have Y tilde equals L minus L bar. L minus L bar is minus QF. And V minus V bar is 1 minus QF. And that's all times XF plus XFF. V minus V bar is again 1 minus QF. And this is going to simplify quite nicely. So these F's all cancel. And we get that Y tilde equals minus Q over 1 minus Q XF plus 1 over 1 minus Q XF. And just a little bit of extra algebra there. What do we have here? We can just combine the numerators there. Y tilde equals 1 minus Q XF over 1 minus Q, or Y tilde equals XF. So when X tilde equals XF, Y tilde equals XF. That means that this is a third point in our calculation that's actually on this 45-degree line. So XF, when there's a line that delineates the condition of the feed called the feed line that we derived back here, the feed line. And this feed line tells us the passing stream relationship for the feed. And now we know that one point on that line is XF. Okay, so this one that's on the 45-degree line. And therefore, the various conditions of the feed are going to have various slopes of a line that depend on Q. So going back to here, L minus L bar is minus QF. V minus V bar is 1 minus QF, just using the terms here in red. And the slope is only due to Q. And we can get the third sort of kind of line that helps us to decide the condition of our column. So just going back here to our summary of constraints, the quality of the feed, we've now defined it, but we can also use that to determine the slope of the Q line. Here's the Q line. So we're quite a ways along here. There's an upper operating line that goes from this point, which is XD, and it has a slope of L over V, which we'll talk about in a second. And it has to intersect with the Q line, which is determined only from Q. And then there's a bottom operating line that has to intersect where that upper line hit the Q line. And that operating line gives us the mass condition for the lower half of the column. Now that we have all those pieces, we're ready to go. So here's the problem that we want to consider. Okay, we have to consider a problem that's related to the design of a distillation column. So we want to find the number of equilibrium stages in a distillation column, given the feed conditions here, both the Q and the composition and the molar flow of the feed, plus the compositions of the distillate and the bottoms, the column pressure, which allows us to look up the equilibrium curve. This is just a made up equilibrium curve that I'm using for the purposes of this discussion. And then we need to know the condition of the feed. And then here's the final little piece of information, the reflux ratio. So the reflux ratio is related to how much in this upper topmost unit, how much of the distillate stream, which becomes fully condensed, is actually returned to the column. So that is the typical last piece of data that is specified in the column. And so this, in the constant molar overflow case, that is just L, as always, the liquid stream that goes down the column. And L over V is the reflux ratio. And I just picked 1.625 so that we could demonstrate the calculation. All right, so here it is. So we know the top of the column, and we're going to use this equilibrium curve. We've defined everything that we are planning to use in terms of things that can be expressed on this XY plot. So at the top of the column, We have a point here, which is xd comma xd. And that top of the column is put into a total condenser. So in a total condenser, so this is stage 1. And we have the stage 1 has x1, y1. And so here's a stream with y1v. And here's a stream with x1l. And this stream goes into a total condenser and becomes the distillate stream. And here comes the reflux. And this is an L stream. And then this is the V stream that came from the next immediate lower stage. And it has the composition of the next immediate lower stage, which is X2. So I'm just going to check off the things we know. We can do the overall balance to get the total flow of the distillate. We were given the molar composition of the distillate. We know because this stream is Y1 totally condenses, it must have the composition XD, so we know Y1. Because we know the reflux ratio, so the reflux ratio is L over V, and we know that number. We picked it to be 0.625. So that reflux ratio is what it is. We also know, we know Y1, so that means we know this Y1. If we know this Y1, we know the composition that's in equilibrium with Y1. So this is XD is equal to Y1. So this Y1 here is also X equal to XD. And the liquid that's in equilibrium with that is the one that comes off of the equilibrium curve here. Right here. So when I read the curve, and I'm not unfortunately going to be able to do it too well, but anyway, this is the composition that's in equilibrium with that first Y. I don't know what I did. Oh, I think I must be underneath here. There it is. Okay, so that's X1. So this must be X1. Now we know X1. And we're done with that column. And then we have to proceed on to stage 2. So in stage 2, we have X2 in equilibrium with Y2. Coming down from above is X1L. Going up is X2V. Coming from the previous stage is X3V. And going down is X2L. So again, just taking an inventory of what we know. We know X2. Excuse me, we know X1. We know X1. Then from the passing stream calculation, so this passing stream calculation, this mass balance, if we know one of the two passing streams, and we know X1 up here, then we know the other one. So I wrote an X here, and that should have been a Y, my mistake here. All the vapor streams are Y's. So this is Y2, Y2, Y3. So this X1, Y2 relationship is just this operating line for the upper half of the column. So here, so we have X1, here's X1, and we need the operating line. Okay, so if we take this expression for the operating line, the slope is L over V, which we know that's the reflux ratio. And we know from a previous calculation we did in the first video that the operating line goes through the point XD here. So this slope is going to be the reflux ratio, 0.625. So I set this up so that I could draw this operating line, put a little dot there to help me with this. And so all I'm doing is drawing a line of slope 0.625 that goes through this point XD, which is on that line. Okay, so we started here in stage 1. And then we're trying to go from stage 1 to stage 2, right? And we need the passing stream. So Y2 must follow right there. It must be on the operating line. So here's Y2. So this is just a graphical way to stick that number into the equation. So here's Y2. So we've just created kind of a step. And now we know Y2. If we know Y2, it's in equilibrium with X2. So that means that Y2 in equilibrium with X2 is this point right here. So this point must be X2. And that's the conditions of the second stage. And then onward. So every time we go from one stage to the other, we get a Y, we get the X from the equilibrium. Then from the X, we get the passing stream. And from the passing stream, that was in equilibrium in the stage below. From the equilibrium line, we get the X. And then from the X, from the operating line, the passing stream, we get the Y from the stage below. And the way it looks on this plot is a series of these kind of steps. So here was the original condition at the top of the column. And then we went and found the Y in equilibrium. Then we went down and found the operating line. Then we went to find the Y that was in equilibrium. And then we come down and find the operating line, and we keep going. Now, when do we stop? Well, eventually we have to get to the feed tray. And I'm just going to say that, well, we can calculate the slope of the feed line from this Q, and you can work that out a little bit yourself, but we end up with a slope of -1. So my feed line will be something that has a slope of -1. So that's a slope of -1. So there's the feed line. And then the bottom operating line goes from the point XB, okay, which is we showed in the first video was on the operating line. And it must intersect at the same spot that the feed line intersects with the first operating line. So now we just, and I'm just going to be a little bit quick about this. Now we know how to finish the whole problem. We continuously step off to equilibrium stage, to the mass balance, to another equilibrium stage. And when I get the chance, the first chance I get, I'm going to switch from the upper to the lower operating line. Now I'm going to go on the green operating line because I have passed, once I pass the red, I've passed the feed plate. So I'm not being super neat here, but you get the idea. I can step these numbers off and counting the number of trays as I continue going in the same manner here. between passing streams, equilibrium streams, passing streams, equilibrium streams, clickety click, all the way to the end of the column. If it doesn't land exactly, then you have to round up, okay? So 3, 4, 5, 6, 7, 8 trays with the feed coming in at the 4th tray. So I hope you find that helpful. That's the McCabe-Thiele system. So thank you very much.